The quantum model of the hydrogen atom. Now we will move on to the formal quantum treatment of the hydrogen atom, and we will compare this result with the Bohr model. So first of all, we will consider the problem in spherical coordinates where r is the radial component, theta is the azimuthal, and phi is the polar. So we will find the wave function as a function of radial distance r, azimuthal angle theta, and polar angle phi. Now, in order to solve this problem, first thing we need to do is to identify the potential energy. The potential energy function for the hydrogen atom is due to the orbit of the electron around the nucleus, and it has a Coulomb potential, which is minus ke square over r, because this is due to the interaction of the electron with the proton in the nucleus. So we have a positive E and negative E product, so that gives us a minus ke square over r potential energy. Then next task is to write Schrödinger's equation. Now if we write this in partly in Cartesian and partly in spherical coordinates, you would have minus h bar square over 2m, a second derivative of the wave function with respect to x, plus second derivative with respect to y, plus second derivative with respect to c, plus potential energy u multiplied with the wave function is energy times psi. Now I'm moving on to the spherical coordinates here, so that I have r radial dependence, theta azimuthal dependence, and phi polar dependence. Now these solutions are separable such that we can write the radial solution to be capital R, the azimuthal solution to be f, and a polar solution to be g of phi. And at the same time, we can recognize some boundary conditions. First of all, as the radius goes to infinity, we should expect that the probability of finding the electron should decay to 0 at infinity, so that the radial solution should decay to 0. And also it should be a finite solution as r goes to 0. At the same time, if you look at the polar angle phi, if I go from phi equals to 0 to phi equals 2 pi, I should have a periodic situation. So g of phi plus 2 pi should be equal to g of phi. So these are some boundary conditions one has to consider. So when full set of boundary conditions is considered, is applied, we obtain three quantum numbers. The radial solution gives us n, the principal quantum number, which has values 1, 2, 3, etc. It's an integer, positive integer. The corresponding energy levels are given by minus 13.606 electron volts divided by n square, where n equals to 1 is called the k shell, n equals 2 to l shell, n equals 3 the m shell, etc. So the energy levels are identical to those obtained in the Bohr atomic model. Now, if I look at the azimuthal solution, f of theta, that gives me another quantum number, L, which is called the orbital quantum number. And this L can take values between 0 and n minus 1. So it's 0, 1, 2 up to n minus 1. How many possible values do we have here? N possible values for L, the orbital quantum number. L equals to 0 is called the S subshell, L equals to 1 is the P subshell, L equals to 2 the D subshell, L equals 3 the F subshell. The polar solution, G of phi, gives us another quantum number, which is M sub L. It's called the orbital magnetic quantum number. It can take values between minus L plus 1, 0, 1, all the way up to L minus 1 and L. So this gives us a total of final value L minus the initial value minus L, 2L plus 1 possible values, because we have also 0 here. Okay, so we have seen that solving the Schrödinger equation for the hydrogen atom, considering the Coulomb potential of the electron due to the existence of the proton at the nucleus, we find a radial solution, azimuthal solution, and polar solution. The solution is separable, and applying the proper boundary conditions such as the radial function should go to 0 as r goes to infinity, finite as r goes to 0, it should be periodic with phi, etc. We obtain three quantum numbers and the principal quantum number from the radial solution, which gives us the energy levels minus 13.606 over n square. K shell, L shell, M shell, etc. correspond to n equals 1, 2, 3 respectively. The azimuthal solution gives us the orbital quantum number taking values between 0 and n minus 1, which gives us S, P, D, F subshells, etc. And the polar solution gives us the orbital magnetic quantum number M sub L, which can take values between minus L to plus L to L plus 1 possible values. So let's consider an example, the n equals 2 level of hydrogen. For a hydrogen atom, determine the allowed states corresponding to the principal quantum number n equals 2 and calculate the energies of these states. So n is equal to 2, remember, is due to the radial solution, and due to the azimuthal solution, we have L, the orbital quantum number, which can take values 0 and 1 up to n minus 1, and the polar solution gives us the magnetic quantum number M sub L, which can take values between minus L and plus L, so it is minus 1, 0 and 1. So the possible states are n equals 2, L equals to 0, corresponding M sub L value is equal to 0. Then we have n equals 2, L equals 1. The orbital magnetic quantum number M sub L can take values minus 1, 0, 1. So we have 4 possible states here. 4 possible states. Discrete set of quantum numbers. The corresponding energy is the same for all of them because n is fixed and the energy levels are given by minus 13.606 eV divided by n squared, so it is 2 squared, and this gives us an energy for n equals 2 minus 3.4 electron volts. So that's basically the energy of all of these states. They have the same energy because the energy levels are determined by the principal quantum number n. So for the n equals 2 hydrogen atom, we have L, possible L values 0 and 1. If L is equal to 0, M sub L can only take a value of 0. If L is equal to 1, M sub L can take values between minus L and plus L, so minus 1, 0, 1. So 2, 0, 0, 2, 1, minus 1, 2, 1, 0, 2, 1, 1. Total 4 possible states. Corresponding energy is minus 13.606 divided by principal quantum number squared, that is minus 3.4 eV. And remember that n equals 2 is the L shell, so it's n equals 1 is the K shell, so this is the L shell, and L equals to 0 is the S subshell, L equals to 1 is the P subshell. So we have L shell here, possible subshells S and P subshells are possible, and the corresponding M sub L values are also listed. So if we use this terminology here, it's L shell with the S and P subshells present in the n equals 2 level of hydrogen.